Hello everyone. So today we're going to try to finish up 10.2. So I just have one more example to show you. So hopefully today's video should be relatively short. So let's get to it. So the next example I want to show you would be a problem in physics where we're going to use differential equations to try to solve for something. So here we go. Let's see if we can and copy and paste this question for us. So let's see if this works. Oh, there you go. Okay, so it looked kind of weird. This last thing right here is r sub 0, which is the a radial distance. Okay, so I'll show you what happened is. So here, a satellite moving along a radial line away from a planet. So here, think of the satellite is like a rocket shooting off the planet Earth. In order for it to actually escape into space, it must maintain a speed that pass what we call the critical escape speed of Earth. So what we're going to try to do is try to figure out what this speed is at any distance from the center of the Earth. So this is how it works. I'll show you a picture to kind of illustrate. So imagine here's our blue planet, or green planet, I guess, I don't know, Earth. And let's say somewhere over here is the center of the Earth. And let's say we have a rocket. Okay. And this rocket's starting at this distance from the center of the Earth. Oops. Oh, okay. I miss. All right, let's try this again. So maybe I'll start from this side. So let's say this distance right here is basically the radius of the Earth. And we're assuming that the rocket would start on ground level, I guess. And it will shoot out at some kind of initial velocity at that point. And what we're going to try to do is to figure out what would be the velocity it need at that moment in order to have enough velocity to carry off the planet. So therefore, at this point, we go probably shoot off the rocket at some kind of initial velocity v sub 0 at this distance, r sub 0. And then the rocket, it going to fly up and hopefully have enough speed to escape the Earth gravity and into space. And that's what we go try to figure it out. And of course, as it move away from the from Earth, it will have a greater distance r with some kind of velocity at that point. So the key is to try to figure out what would this initial velocity be, this v sub 0 need to be, in order for us to actually allow this thing to fly off the planet Earth. All right. So let's go and try to figure this out. So what this scenario describing is that as this rocket changing the r value, as it moves away from Earth, its probably velocity will also be changing based on some kind of initial velocity that is lift off from the ground, v sub 0, at the surface of the Earth, which is r sub 0 away from the center of Earth. So let's see if we can actually use something we know to figure out how this whole thing work out. And you realize that even though this seems like just such a simple concept of, okay, you need to go fast enough to escape the Earth, that seems obvious, but the question is how fast. It's actually not that easy to calculate. So let's try to figure this out. So how do we figure this out? Is by first start to understand that the reason why we need a certain speed to escape the Earth into space is because we need to somehow overcome the gravity. So therefore, we must first know what is the gravity involved. So gravity is given by this formula from physics. So hopefully I didn't get the wrong formula from physics. So physics, I learned that F, the force due to gravity, is given by the formula negative G, which is gravitational constant, multiply the mass of, I guess in this case, the Earth, and the mass of the rocket over the distance between them, which is r squared. So in this expression right here, obviously our F is our force, which is what holding things onto Earth. G is basically a gravitational constant. I have no idea what this number is. I usually have to look that up. Some of you might know off the top of head what it is, but I don't. But it is some kind of constant, gravitational constant. Capital M, I guess we can say this is the mass of the planet Earth, which exert the gravitational pull. And lowercase m would probably be, in this case, the mass of the satellite or the rocket that we try to have it escape from Earth. And obviously r is the distance between the center of the Earth and the rocket, which in here we're going to call that the radial distance, because it's basically stemmed from the center, so act like a radius. All right, and of course here the important part is that there's a negative, because that is actually act in the opposite direction as the radius. So as the rocket move away from the center, r would be increasing. The gravitational force would actually pull the object backward. So that's one thing. Number two, interesting to note is that this gravitational force follow what we call the inverse square law, because it's inversely proportional to, or is actually relating to 1 over r squared, where in this case F and r are the two variables involved. Because the force in here, the G is a constant, the mass of the Earth should be a constant, the mass of the satellite would be relatively constant, which technically speaking is not, because as you fly, you will be burning fuel, and therefore make your rocket or your satellite less heavy. But we go assume that that is negligible, that we're not going to concern about that, because we don't want to introduce another variable in the system. If we just assume the maximum mass of the satellite, and if the escape velocity can allow it to escape, then obviously any smaller mass would still work. So therefore, we're not going to assume that would change. So therefore, in this entire equation, there are only two variables, F and R. So in this case, F is our dependent variable, R is our independent variable. As R changes, the F would change. And as a matter of fact, because the inverse R squared, therefore meaning that the bigger the R is, the smaller the F is. But the negative still allow it to point back toward the center of Earth as the force at the direction. So how do we actually proceed with figure out this formula? Because I mean, from first glance, this formula does not seem to relate to anything about derivative. But that's not true, because you learn Newtonian physics. And Newton's law of motion dictates that any object that's under some kind of force must accelerate. And when they accelerate, the force exerted on the object is actually relating to the mass and the acceleration of the object. Which means in this case, in this formula, F equal to negative gmm over r squared. In this formula, F is also equal to mass times acceleration. And in this case, I can represent acceleration as a second derivative of the radius, d squared r over dt squared. And now allow me to set this formula, ma, equal to our gravitational formula, and have this formula, m d squared r over dt squared is equal to negative g, capital M, lowercase m, over r squared. And notice automatically the mass of the object now no longer matter. Okay, so therefore, even if that mass is changing, which actually if it's changing, it might complicate things a little bit. But since we're going to assume that it's constant and we're not going to worry about the fuel get burned off or things like that, I'm now allowed to cancel them out and now have it equal to that. So now the next thing is, so that's good, but that's a second order differential equation. And also not to mention is that this differential equation has a t involved. And I really would rather not have a t involved. So what should I do? So here what I'm going to do is I'm going to do a little trick. I'm going to do a little trick to try to manipulate my system to try to solve this. Because right now what we have is a second order differential equation, which is not that easy to do. As a matter of fact, we don't know how to do that yet. Second order differential equation. Because of the d squared r over dt. So what I'm going to try to do is I'm going to try to figure out something to simplify it. And if you think about it, notice that what we try to figure out is a relationship between r and v. So maybe in some way I can try to figure out, is there a way to can relate those two things together? And of course there is. So this is how it works. If I think about it, I'm going to go ahead and let the velocity equal to dr over dt. Which makes sense because velocity is basically changing distance versus time. And in this case, r is basically the distance that the rocket is going to travel. And if I find out how it changed versus time, that would basically be what velocity is. And interesting thing enough is if v is equal to dr over dt, then I can say d squared r over dt squared is basically just the derivative of v, which is basically dv over dt, which is nice. But of course there's a problem. The problem is I want to avoid using t. Remember, what I want is a relationship between v and r. So I have to somehow get rid of the t. So how do I do that? I'm going to do a little trick. I'm going to then try to find out using what we want as a chain rule and say that dv over dt should equal to dv over dr multiplied by dr over dt. And notice that if I write this way, the dr technically kind of cancel out. And the beauty of that is, what is dr over dt? That is actually what we define to be v. And therefore, allow me to write dr squared over dv squared as actually v dv over dr. And that allows me to define a derivative relating to v and r, with v and r being our variables. We don't really want to have the t involved because we're not looking for the relationship between v, r, and t. And having that t as a parameter relating to both v and r together, you're just going to complicate the math. So by doing this process, now allow me to actually bypass t and just talk about how v and r affect each other. So therefore, I'm going to now replace d squared r over dt squared as v dv over dr equal to negative gm over r squared. And believe it or not, this is now a separable differential equation. So despite all this thing, the equation they come up to actually is not that difficult to do because it is separable. So how do I separate? So in this case, the equation already separated by itself. We have this right here, which is technically our g of v. And we have this right here, which is technically our f of r. Okay, yes, I didn't use g of y because in our case, y is the independent variable, is v. So v plays the role of y. And then r plays the role of x because r is the independent variable. And if you're thinking, how do I know that? Because of the derivative. V on top, that's dependent variable. R on the bottom, that's independent variable. So now I can actually just form this integral. Now, because of the fact that I'm looking for what's happening from this point, which is our initial condition, R sub 0, V sub 0, I'm going to do things slightly different and form this differential equation as this. By forming, instead of a indefinite integral with the integration constant c, I'm going to go ahead and deal with that directly by putting the initial condition into my equation. And yes, I know some of you might be thinking, like, is it proper to have the dv and v and then use v in the limit? Not really, but here I'm going to just keep track of it because I just don't want to change these two variables inside. It might get too confusing. So now this side should be easy to do. If I integrate this side, what I have would be just 1 over 2 v squared, evaluate from v sub 0 to v. This side requires a little bit of work. I'm going to take out the negative gm, integral from r sub 0 to r, and I'm going to write it as r to negative 2 dr, so that way I can integrate properly. So if I integrate that, that becomes negative gm. Integral r to negative 2 is negative 1 r to negative 1. So therefore become just negative r to negative 1. Evaluate from r sub 0 to r. So therefore, if I now plug everything in, I will have 1/2 v squared minus 1/2 v sub 0 squared equal to negative gm times this thing right here, which become, I'm going to just write it right here. Well, actually, as a matter of fact, I'm going to go and do this first. I'm going to get rid of the negative here because the negative and the negative become positive. And this r to negative 1 from r to r sub 0 will be 1 over r minus 1 over r sub 0. So therefore, this becomes gm over r minus gm over r sub 0. So now I have an equation that relate v and r together. And some of you might realize, if I look at this right here, notice that this is the integration constant on the left, this is the integration constant on the right. That's one of the beauty of putting the initial condition into your limits as you're doing the integration. Instead of using an indefinite integral, use a definite integral and use the initial condition. Therefore, automatically you calculate the concept of integration directly. So now that I have this equation, now what? Well, remember what we're trying to figure out is what is v sub 0 in this scenario based on where r sub 0 is, because r sub 0 is where the surface of the Earth is, and that's where we go launch the rocket. So when the rocket get launched, that is where he has to achieve the critical escape velocity at that point, so he can propel it fast enough and strong enough to overcome the Earth gravitation pull and escape into Earth. So how do we figure it out? So, well, how about we do the following? So first thing I'm going to notice is this. If I'm looking at this equation right here, remember I'm trying to find a relationship between v and r, where v is our dependent variable, r is our independent variable. So what I'm going to do is let's basically solve for r first. So if I do that, what I'm going to do is I'm going to go ahead and multiply everything by 2. And then I'm going to move the v sub 0 square over. Actually, I'm going to rearrange it this way. The reason why, because v sub 0 is a constant. Remember, v sub 0 is the escape velocity, which is a constant. So r is actually the variable right here. So I'm going to keep the r in the front. And then plus v sub 0 square minus 2gm over r sub 0. So if you look at this right here, okay, notice the following. What I'm going to do is I'm going to go and take the square root to get v. Now, technically speaking, when I take the square root of this entire equation, I do have to consider plus or minus. Remember what Mr. Bernhardt said? When you take the square root of v squared, you tend to have absolute value of whatever it is, and therefore result in plus or minus. But in here, we are not considering the negative velocity as an answer, because that would mean that the rocket is shooting toward Earth, toward the center of the Earth, which that's not what we try to do. So I'm not going to consider that. So I'm going to just say, in this case, I'm going to say v has to be a positive number that take the form of square root of 2gm over r plus v sub 0 square minus 2gm over r sub 0. Good? So now here comes the interesting part. So we know that v has to be positive, but notice that v is also underneath the square root, and that becomes interesting. The reason why it's interesting because in order for v to actually have a value, what must be true is that what's underneath this radical must be positive. Otherwise, we would not have a v value. So therefore imply that 2gm over r plus v sub 0 squared minus 2gm over r sub 0 must be greater than 0. Now, second things I notice is the following. As r increases, meaning as the rocket continues to move further and further away from Earth, 2gm over r would approach 0 because r on the bottom continues to get bigger. Now, of course, realistically, r is not going to get too big before it escapes Earth. Okay? But regardless, that number continues to get smaller. And because of that, what I probably want to do is to make sure that this part of our formula, which is the constant part, to at least be bigger than 0 to begin with, because this part is always positive. Approaching 0, but it's a positive value that approaches 0, meaning as r increases, this value gets smaller and smaller. Okay, so if I can maintain that this part is bigger than 0, then I can guarantee that I have a positive number plus some positive number, and therefore it would always be a positive number bigger than 0. And if this part of the number somehow become negative, and it's this number getting smaller, then there is a possibility where this number plus this number become less than 0, and that become impossible for us to get a v. So that's what we want to avoid. So therefore, meaning at the bare minimum, what we need is that for this part, v sub 0 square minus 2gm over r sub 0 to be positive also. And if that's the case, then we'll have a positive number plus a positive number, therefore guarantee what we have under the radical would be positive. Now, of course, realistically, there is some wiggle room, because as long as this part is, even if it's negative but smaller than this part, will still be okay. But as this gets smaller, we don't want to run the risk. So therefore, we just will require this part to be bigger than 0 to make sure that we have more than enough critical escape speed to escape the Earth. And now that allows me to now figure out what v sub 0 is. V sub 0 would then equal to this. V sub 0 squared must be greater than 2gm over r sub 0. And therefore v sub 0 must be greater than the square root of 2gm over r sub 0. So what I'm claiming is this is the critical escape speed. Now, of course, I don't know what this number is, but at least I now have a formula to generate it. And now it's just a matter of knowing what gm and r sub 0 would be. Then we're good to go. Unfortunately, I don't know what they are. So what I'm going to ask you to do is to, after you finish the video, go online and look up gm and r sub 0. So g is the gravitational constant. Make sure you pay attention to the unit, because you need the unit to be consistent with the m and r sub 0 that we use. I would say that m is probably going to be in kilogram. Okay, that's the mass of the Earth. and then r would probably be the radius of the Earth. Now, which I do know that the radius of Earth slightly in different spot, because our Earth is not a perfect circle, a perfect sphere. So, but you can kind of pick, I don't know, the radius on the equator, which is probably the furthest. Or if you want, you can find what is the shortest radius on Earth and use that, because the shortest radius would yield the larger critical escape speed, therefore will probably be safer that way. So I'm going to let you figure that out. And if you want, you can definitely tell me the answers when we talk about it during class. Okay, that is it for this video as well for 10.2. So exciting, 10.3 is where we go first, start to talk about some differential equation that you haven't learned how to solve. So that would be exciting. Okay, so hopefully you're looking forward to it as I am. All right, talk to you later. Bye-bye.